Hello everyone. Today I am in Raleigh for another field trip, and you guys are in the classroom learning about wave behavior. So I'm going to go ahead and talk about it. This will be the last lecture before we get into more specific types of wave behavior next week. When we start talking, I believe, about acoustics. Actually, not next week. Next week we'll be on vacation. The week after next week. We're going to talk about different things that occur to waves as they're moving through space. Now, we've talked about the definitions of waves. We kind of have to find periodic motion in general. The first behavior of a wave we're going to talk about is reflection. And this is just waves bouncing off of a surface. If you've ever played putt-putt, you know what reflection is. You hit the golf ball towards the hole, and if you try and make a bank shot off of the side of the green, then you're going to have to figure out what angle you're going to have to hit the golf ball at off of that corner in order to hit it into the hole. Now, I've tried this many a time, and I've usually failed. There was one game that I did pretty well, and this is, if you are good at putt-putt, it's because you understand either deliberately or unintentionally the law of reflection. And the law of reflection states that the reflected angle of a reflected wave is equal to the incident angle. Now, that's a lot of big words, and we need to define some of those words. So what is a reflected angle? The reflected angle is simply an angle that is coming off. It's the golf ball after it's hit the side of the putt-putt green. So it's been reflected. It's no longer traveling in the same direction that it was when you putted the ball, right? The incident angle is the incident when the golf ball hits the side of the putt-putt green. So as the ball rolls up to the side, it hits that side, then pops off. That angle is the incident angle. Now, the incident angle and the reflected angle, according to the law of reflection, are always going to be the same thing. So what you want to do, whether it be in putt-putt or pool or billiards, you want to hit the ball at the side or the corner at the same angle that you want that ball to go into either the pocket or the putt-putt hole. So it does have some practical applications, at least in your free time it does. There's different types of reflection. One is called specular reflection, and that is a clear image from a mirror, because light itself can reflect. That's what mirrors do, they reflect. So specular reflection is when light essentially is coming at you with a purpose. It's organized. All the photons are bouncing off in tandem, bouncing off of an object surface in tandem. Specular reflection is involved in seeing any object that doesn't emit its own light, as it is through sunlight reflecting off of objects that we can see them. So most things have some degree of specular reflection. There's another type of reflection called diffuse reflection, and that is when light is scattered. So everything gets jumbled when it's bouncing off of the surface. So that is reflection. Reflection is when things bounce off of a surface. The other behavior that waves exhibit is called refraction. And this sounds a lot like reflection, but it's not bouncing. It's when something passes through a different medium and it changes speed. So whatever wave it is, it changes speed. This most often is in the case of light. So remember yesterday we talked about how light always has the same speed. But there's a caveat to that. Even though light always has the same speed, if you put it in, like, say, a diamond, the light is still going to move from point to point as fast as it ever has, but it's going to be slowed down into how far it can get, how quickly it can get through the diamond, not by its speed, but how many times it has to bounce off of the different points. So it's going to start to go through the diamond, bounce off of a surface, go to another surface inside the diamond, bounce off of that, and just keep on bouncing from crystal to crystal to crystal. And in that way, it's going to slow down the speed of light, the practical speed of light. So I guess it does have some reflection in it, but refraction is kind of like the compounding of all those different reflections. It's when you slow down something. And when you slow down something as it enters a medium, it tends to refract. It tends to bend. The motion bends. So if you put a light through a diamond, and it's possible to actually see the light moving through the diamond, you'll notice that it will start to bend. The light will. So instead of going in a straight line, it'll come up to it, hit it, and then have an angle of reflection down, or an angle of refraction. This is why when you look at a fish bowl, like a fish in a fish bowl, the light gets distorted. It's because light, when it's entering the water, refracts. It changes its speed because it's bouncing from one water molecule to another water molecule. Keeps on bouncing off of the different water molecules, and it changes its rate of flow. It changes its speed, its practical speed. You can think about refraction again in putt-putt. So if you have a hill, there's a different speed that the golf ball will go uphill at, as opposed to when it's just lying flat on the ground. So if you hit a golf ball up a hill as you're putting, it will tend to bend one way or the other. That's because as it's going upwards, its speed decreases and it refracts. So it has a curved pattern rather than a straight one. Same thing if it goes downhill. It tends to speed up, so therefore it has a curved pattern. Snell's law is a mathematical equation that describes how the wave changes direction as it moves into a new medium. And that's just a name you need to know, Snell's law. Ocean waves are refracted by the ocean bottom to turn the waves parallel to the shore. So that's why when you go to the beach, the waves aren't coming in necessarily directly up to the beach. If you look at the coastline, they actually are coming in at an angle. Okay, so that's reflection, refraction, and the final one, I think, is diffraction. And this is the bending of waves around an obstacle or through an opening. You can think of just a big rock out in the ocean, and as waves are coming up to the shoreline, they have to kind of encase that rock, and it splits apart the waves, and the waves have to accommodate that big rock. That would be diffraction. Interaction between the wave and the obstacle or edges of the opening causes the wave to change direction. Light can be diffracted if the obstacles are small enough. Diffraction grating is having thin lines etched in them that diffract lasers. So it's just, diffraction grating is just a practical application of diffraction. Tombolos is a landform that connects an island with the shore, and they develop because of the refraction and diffraction of ocean waves. Again, think of a big rock out in the ocean, and the waves are trying to crash around it, causing diffraction. Interference. Interference is another wave behavior, and it's the combining of waves where they overlap. And you can have two types of interference. There's constructive, in which waves are built up, and destructive, in which waves are torn down. So you can think of noise-canceling headphones. So waves go generally this pattern, right? Up and then down and up and then down. You can build waves upon waves. You can add waves and you can subtract waves. So yeah, say you have a crest that's followed by a trough. That's one wave. Your second wave is a trough followed by a crest. If you add these waves together, they will cancel each other out. And that's how noise canceling headphones work. They sense sound in their environment and they create waves with opposite amplitudes so that the waves just cease to exist. It's kind of cool. Now, constructive interference, so that would be destructive interference. Constructive interference can be thought of in a choir. So people think, why do I sound good in the shower? Well, the truth is you don't. You don't. I'm sorry to tell you this. But the reason why you think you sound good in the shower, besides your own arrogance, is because when you sing, the notes that are good have a certain wave pattern to them. When they bounce off of the shower, just due to physics, those good notes tend to build on each other. And they build and they build and they build as they start to echo off the sides of the shower, which is a very echoey place to be. And so you sound a lot better because all of your bad notes are canceled out. Same thing in a choir. Choirs are invented because most people are singing at any random moment the correct note. So it turns out that their good notes deconstruct the bad notes, or at least they build on top of each other over and over and over again, to where, in general, everyone together sounds good, even if one particular person doesn't. So it is kind of cool. A standing wave. This is a wave that is moving even though the locations of the crests and troughs appear to be stationary. Two identical waves of a specific wavelength moving through a medium in opposite directions can cause a standing wave. The length of the medium must be a multiple of 1/2 of the wavelength. Nodes are 4 locations that don't seem to move at all, and the antinodes are the location of the crests and troughs, so there are points of maximum motion. The Doppler effect. This is the apparent change in frequency of a wave due to the motion of the source or receiver. Christian Doppler, a Danish scientist, described this phenomenon in 1842, and this can be used to explain why police cars and ambulances' sirens change pitch as they move. So if you have a siren and it's coming towards you, it's sending out sound waves at a certain frequency. Now, as it's coming toward you, it's constantly getting closer. So the amount of times those frequencies hit you actually increase. So the frequency is rising. Now, frequency is related to pitch. They're the same thing. So if something's frequency increases, the pitch will increase, making a higher tone, the pitch higher. So when it's coming towards you, the siren goes up in pitch. When the siren is going away from you, it's still sending out sound waves, but it's sending them out further and further away from you, so that as it gets further and further away from you, the pitch decreases, because the frequency of when those sound waves hit you decrease. And we figured out how to use this idea in terms of earthquakes. We can shoot out some type of wave and then see when it comes back to us. That's another use of the Doppler effect. We use this in terms of radar. So you have Doppler radar. So we send out an electromagnetic pulse, and then it comes back to us. And the frequency at which it comes back to us at lets us know how far away things are. And that's it. Okay, so I want you guys to read page 415, perform the wave behavior summary, and perform section review 17C. And I'll see you guys tomorrow. Thank you.